So for number one, the first thing that I would do is use one of my odd-even identities, specifically odd-even number 4. That allows me to write cosecant of negative x as negative cosecant of x. And then I'll use reciprocal identity number 4. That's going to be sine of x times negative 1 over sine of x. And that just simplifies down then to negative 1. For number 2, I would use the Pythagorean identity P2. So cotangent squared is 1 plus cotangent squared, and the negative 1 distributes, and you're left with cotangent squared minus 1 minus cotangent squared, and boom boom, and that gives us negative 1. Those two hopefully were pretty easy. This one was a bit more challenging. So here, what I would do is use Q1 and Q2 to rewrite cotangent squared as secant squared over cosecant squared, and then that's all over cosecant squared. Similarly, I can write tangent squared as cosecant squared over secant squared, and that's all over secant squared. Did I write those down in the right spots? I did both. These are in the wrong spots. My apologies. I was like, that's not right. Cotangent is supposed to be cosecant squared over secant squared. That's much better. And then this is supposed to be secant squared over cosecant squared. My apologies. So when I reduce these, I'm left with 1 over secant squared plus 1 over cosecant squared. If I apply R1 and R2, I get that's cosine squared plus sine squared, which is just 1. So that's that. Okay. If you don't feel great about these quite yet, that's okay. We'll do some more practice yet. Not quite right now, but we will do some more work with these kind of problems. Either is fine. Whatever is most convenient for you. P.S. You're wearing 2 different socks. That's okay. Yeah, sure. Okay, let's take a look at the assignment from last time. That was 15 through 30. So let's take some questions here from that. So we'll take, 20 minutes or so of just take some general questions from you guys, whatever you guys want to talk about. Valerie? 17? Okay. We want to solve tangent of x is equal to 1. So to get x by itself, we'll just do tan inverse of both sides. And now what I want to do is go to the unit circle. So remember, on the unit circle, tangent is y over x. That's a different x than the variable x up there. I know that's confusing. So I need a place where y over x is equal to 1, or really a place where the x and y have the same coordinate. So if I go to my unit circle and look, that happens at pi over 4 and at 5 pi over 4. So that's my answer for part A. For part B, we want all real numbers of x's. So it's tempting to want to write this as this, and just tack on the plus 2 pi k's at the end. However, we can do a little bit better than that. Notice that on the unit circle for these, pi over 4 is here and 5 pi over 4 is here. And between those two answers is exactly pi units each direction. So we can take this infinite solutions that we've written as two separate solutions and really just combine that together into a single solution where we're just going up by adding or subtracting pi instead of 2 pi. This is a common feature for tangent functions. Why do you suppose that happens frequently for tangent? What's the fundamental period for tangent? Pi, as opposed to sine and cosine, which is 2 pi. So when you think about it that way, hopefully it's not super surprising. Value okay there? Okay. For part C, we want things between negative 2 pi and positive 2 pi. So clearly my answers for part A will still be there because those are between 0 and 2 pi, right? We now need to worry about things between negative 2 pi and 0, though. So all I'm going to do is find angles coterminal to each of these, pi over 4 and 5 pi over 4, that are smaller. So I'll do that just by subtracting 2 pi. So when I do that, I get negative 7 pi over 4, and then negative 3 pi over 4. And those are my answers from negative 2 pi to 0. So when I take those together, those 4 are everything between negative 2 pi and positive 2 pi. Feel okay with that? Okay. D, we're looking for things between negative pi and positive 4 pi. So definitely my answers for part A are going to be in that set because, well, that's between 0 and 2 pi. Some of my answers from part C will be in there. So if I look at my answers from part C, this one is too small. That's less than negative pi. But this one is fine. It's bigger than negative pi. So that's my answer from negative pi to 0. And then we still have to worry about this stuff from 2 pi to 4 pi. So how am I going to find that stuff? I'm just going to take these two results and add 2 pi to them. I'll find an angle coterminal to each of them that's larger. So when I do that, I get 9 pi over 4 and 13 pi over 4. And that should be my set for part D. Is that okay, Val? So again, I tried very hard to use my results of things I had already gotten in the previous steps to make this process go a little bit quicker. What else did we want to talk about? JJ? Sure. Megs. 19. Okay. So we have cosine squared of 1/2. So to solve for cosine, we're going to square root both sides. And when I rationalize my denominators, that gives me root 2/2. So I'd split that into two equations to solve, and I'd get x is the cosine inverse of positive root 2/2, and then cosine inverse of negative root 2/2. When I go to my unit circle, I have answers at pi/4 and 7pi/4. And then over here I have answers at 3pi/4 and 5pi/4. That's my answer to part A. I know you asked me for just part D, but I can't really do part D without doing at least part A. Okay, so for part D then, obviously all of these solutions are going to be on my list of answers, because all of this stuff is between 0 and 2 pi, and for part D we want things from -pi to 4 pi, right? So all those are in there. Now I'm going to look at the stuff between -pi and 0. To find those, I'm going to subtract 2 pi from each of these. If I subtract 2 pi from that, from the first one, it'll be less than -pi, so I don't want that. If I subtract 2 pi from this, also will be less than -pi, so I don't want that one. This one, the next one though, is fine. And the last one is fine. And then I just have to worry about the stuff from 2 pi to 4 pi. And that's easy to find. I'll just take the first 4 answers and add 2 pi to each of them. So I'd have 9pi/4, 11pi/4, 13pi/4, and then 15pi/4. And that would be my set for D. Is that okay? So if I look at this one and this one, those two answers are pi apart. Similarly, this one and this one are pi apart. So I can write my solution set instead of 4 answers plus 2 pi, I can just do 2 answers plus 1 pi. That's uncommon to happen for cosine, but we've seen that it happens here. Typically that wouldn't be possible. But that's why I did that. Does that make sense there, Meg? And really the only reason this works is because you had the plus or minus and you ended up with 2 equations to solve for. Right? If you don't end up with 2 equations because of the plus or minus, that wouldn't happen for a cosine function. Right. Oh, you should have the other one. Did I just forget one then? So you should have that one, and then that one. And again, it doesn't really matter if you wrote pi/4 or 5pi/4 there. The convention is usually to use the smaller one, but it wouldn't be wrong. And it wouldn't really be wrong if you wrote all 4 of them plus 2 pi k, but it's not like the simplest way of doing it. It's not incorrect. It's still representing the same solution set, but it's just more compact to write it with 2 answers instead of 4 answers. If that makes any sense. It's like not reducing a fraction at the end. Like it's still the right answer, it's just not the best answer or whatever. Who's next? there's one that I want to talk about that I think is the trickiest one on here. That's 27. And 27 is really only tricky because you have to be very careful about the intervals that you're working on. So for part A, we just have one answer, right? So part B, and that just simplifies down to just 2 pi k, where k is an integer. For part C, we want this. Notice here that I have brackets at both ends of this interval. So I have 3 answers here. I have negative 2 pi, I have 0, and I have positive 2 pi. Why isn't 2 pi an answer over here in part A? Because there's a parenthesis here, which is very sneaky, Mr. Kulik. And then for part D, the interval was negative pi and up to 4 pi. So here my answers are going to be 0 and 2 pi. That's it. Why don't I include 4 pi? Because it has that parenthesis there. So this one I liked this one because you really had to be paying attention to the endpoints of those intervals and whether they were open or closed. Because there are lots of answers that are like, oh, it's right at the end of the interval. Do I include that or not? So you had to really kind of pay attention to that here on this one. Where before it hadn't really mattered too much, right? This was, I think, one of the few problems where whether those endpoints were open or closed made a big difference. What do you guys think? Do we need to do another one? Megs? 26? Oh, sure. That makes sense. This is one where there's a nice easy trick to this, but if you hadn't seen that trick before, it's unlikely you'd come up with this on your own. Ready to see the trick? No? This is my trick. Why would I do that? That turns it into tangent. And now this is the same as number 17. I think we did 17 earlier, right? And in a situation like this, if it's on the homework, if you can show it's the same thing as another problem, I don't need you to do it again. Just show that it's the same thing and then refer to the previous answer is perfectly fine. Bridge? Yeah. Yeah, I would use the exact same trick on 29. Absolutely. All right. What do you guys think? Okay. So I want to do a little bit more on solving because there's another situation that we haven't yet talked about when in regard to solving. And it's kind of subtle and tricky, so I wanted to make sure that we had a chance to talk about this. So let's say we wanted to solve the sine of 2x is equal to a half on the interval 0 to 2 pi. At first glance, okay, no big deal. There's nothing wrong, nothing here that seems difficult to deal with, right? We would just say, okay, we'll take the sine inverse of both sides. Then I'll just go to my unit circle and figure out where the y-coordinate is a half. So that happens at pi over 6 and also at 5 pi over 6. And then I'll just multiply both sides by a half. And I'd say, okay, my answer is pi over 12 and 5 pi over 12, and I'm done, right? You didn't get them all. You didn't get them all. So let's explain why. But to do that, I'm actually going to solve this guy first. I'm going to solve over the entire real line first to go back and show you why we didn't get all of the answers on that first example. We're going to come back to that and fill in the missing ones here in a second. But this, I think, doing this one kind of helps explain why we're missing answers. So if I do the same thing, I get 2x is equal to pi over 6 plus 2 pi k, and then 2 over x, or I'm sorry, 2x is equal to 5 over 6 plus 2 pi k. Everybody's okay with that, since we're solving the infinite one? Now, when I multiply both sides by a half, that 1/2 distributes. And my two answers are pi over 12 plus pi k and 5 pi over 12 plus pi k, and again, where k is just some integer. So these two answers are for when k equals 0, right? If I take my infinite answer there and plug 0 in for k, I get those two. If I plug k equals 1 in, I'm going to get 13 pi over 12, and I'm going to get 17 pi over 12. Notice both of those are still less than 2 pi, right? So those should be included in my answers. If I add another pi, though, I'm definitely going to be bigger than 2 pi, right? So that's it. This should be my solution set. The moral of the story is, when you have a coefficient inside or attached to the x, I would find the infinite solution first, and then use that infinite solution to generate whatever answers you need inside the intervals. You can just keep adding or subtracting pi as needed until you end up outside the interval, just like we did here. Does that make sense? Now, here's my question for you guys. Why are we getting, say, twice as many answers here? Geometrically, can somebody give me a geometric explanation of why I'm getting all of a sudden twice as many answers? No? So remember that we can describe the graph of any of these trig functions in this fashion, right? What did the coefficient on x do? It creates a horizontal stretch or shrink. In the case where the coefficient is 2, what we've done is for sine, we took like the fundamental period of sine, and we cut it in half. Yeah, I did a poor job on that. So, for example, if we're at 1/2, how many times are we going to get to 1/2 now with the green graph? 4 times, right? 1, 2, 3, 4. How many times did we have it for the red graph before we did that transformation? 2. So the red graph is where the x coefficient is 1. The green graph is where the x coefficient was 2. You see you're getting twice as many answers. If that x coefficient was 3, you'd expect 6, etc. Right? Everybody's okay with that? Let's do one more example here. So, first thing we would do is need to square root both sides. Then we're going to break this into 2 separate equations. So I get 3x is equal to the cosine inverse of root 2 over 2, and 3x is equal to cosine inverse of negative root 2 over 2. So, if I go to my unit circle, cosine inverse is equal to positive root 2 over 2 at pi over 4 plus 2 pi k, and also at 7 pi over 4 plus 2 pi k, and it's equal to negative root 2 over 2 at 3 pi over 4 plus 2 pi k, and also at 5 pi over 4 plus 2 pi k. And then when I multiply both sides of each of these by 1/3, I'm going to get x is equal to pi over 12 plus 2/3 pi k. X is equal to, I don't know why, 7 pi over 12 plus 2/3 pi k. And then I have 3 pi over 12, which really reduces to just pi over 4. Let's write it that way. Plus 2/3 pi k, and also 5 pi over 12 plus 2/3 pi k. So, I wrote an 8 there. Jeepers creepers. So, That's my solutions when k is 0, right? But clearly 7 pi over 12 is way less than 2 pi. It's very likely that we're going to have some more. When k equals 1, what are we going to get here? Well, I would need to be adding 2/3 pi to each of these to make a common denominator there. 2/3 I would have to multiply to make it 8/12. Everybody agree with that? Okay. So I'd have 9 pi over 12. I could reduce that. I'm just going to leave it the way it is for right now. And then 15 pi over 12, still less than 2 pi. Maybe I should have left that as 3 pi over 12. That probably would make my life a little bit easier. At least I'll reduce it over there later. And that's 11 pi over 12. And then this last one is going to be 13 pi over 12. All of those are still less than 2 pi, right? So maybe I try again. So if I add 8 pi over 12 to this, I get 17 pi over 12, still less than 2 pi. And then I get 23 pi over 12. Again, still less than 2 pi. I get 19 pi over 12. Still less than 2 pi. And I get 21 pi over 12. Still less than 2 pi. Everybody's okay there? And if I do this one more time, obviously everything's going to be too big at that point, right? If I just look at the smallest one, if I add 8 pi over 12 to that, it's going to give me 25/12, which is bigger than 2 pi. What do you guys think? That's okay? We're going to stop here. What I'd like for you guys to do for me next time is to do 31 to 46. Beware of the factoring problems in there. There are several that need to be factored.